Welcome. This video is going to go over the Chapter 1 test from SL Chemistry and take a look specifically at how you should be able to answer a multiple choice question without a calculator and within the 2 minutes that IB thinks it should take you to answer the question. So number 1 wants to know how many molecules are present in a drop of ethanol, and there's a formula for ethanol, and then more importantly, here's the mass that they estimate that drop weighs. So you've got to get from grams to molecules. So immediately you should realize to get from grams to molecules, you need to go to moles and then to molecules. So to do that, you're going to have to find the molar mass of C2H5O6. So you've got 2 carbons, so around 24, 6 oxygens, so now you're around 30, and then 1 oxygen, so this is going to be about 46 grams. And then I've got 2.3 times 10 to the minus third, and 1 mole weighs 46 grams. So now this is where you should be able to see that 2.3 over 46, that's about 0.5, but with the decimals, it's really 0.05, and you still have the 10 to the minus 3. So you can rethink this. This is really 5 times 10 to the minus fifth. And that's how many moles we're talking about. So I've gotten step 1 done, and now to get to molecules, I take 6.02 times 10 to the 23rd molecules per mole, and 5 times 6 is going to be 30. So this is 30, and then my minus 5 and my 23, 10 to the 18th, which is really 3.0 times 10 to the 19th. Number 2 wants to know the mass in grams of 1 molecule. So now you're going the other way. You're trying to go from molecule, you're going to have to go to mole, and you want to end up at grams. So how do you do this in 2 minutes without a calculator? Well, the mass in grams of 1 molecule, so to get that to moles, it is 1 divided by 6.02 times 10 to the 23rd. So I'm just going to leave it as 1 over 6.02 times 10 to the 23rd. And then I'm going to have to multiply that by the grams per mole for ethane. So 2 carbon, 24, the hydrogen. So we're talking about 30 grams. And again, if I take 30 and divide by 6, I'm going to get 5 over 10 to the 23rd, or that really is 5 times 10 to the minus 23rd. Number 3 wants to know which sample has the greatest mass. So the last one is the easiest one because that's 170 grams of iron. So that one is easy to convert. The others all start as atoms or molecules. So you've got to convert them. Well, actually the B is moles, so that one's also fairly easy to convert. 5 moles of neon atoms. Neon, you look, it's 20 grams. So this is about 100 grams. But these other two, we're going to have to get Avogadro's number involved. But look, they gave you really easy numbers to use with it. 6.0 times 10 to the 25th molecules. If you divide that by Avogadro's number, 10 to the 23rd, you're really talking 100 moles here. And then hydrogen weighs 2.02, so we're talking 202 grams. And C, 1.2 times 10 to the 24th atoms of silver. If you divide by 6 to the 23rd, you should get 2 moles here. And 2 moles of silver is just under 108. So we're talking about 216 grams here. So again, very quickly you should be able to come up with C being the correct choice even without a calculator. D, which compound has the empirical formula with the largest mass? Well, the first thing you need to know is the empirical formulas. So I have CH3, CH2, CH, and CH2. So now it's pretty obvious, even without checking molar masses, that A is going to have the largest mass. Number 5, I think, is one of the more challenging questions on the test that I gave you, because it says equal masses of the metals Na, Mg, Ca, and Ag are added to separate samples of excess HCl. So the first thing you have to realize is that Na has a mass of about 23 grams per mole, Mg is 24.3, or about 24, we could probably round to. Calcium's around 40, and silver's around 108. So if you have equal masses of each, Na and Mg have more moles in equal masses than either calcium or silver. Silver's going to have the fewest moles. But then they made it a little ickier for you. They also said they want to know which metal produces the greatest total volume of H2. Well, if you look, you realize Na and Ag both have an oxidation number of +1, whereas Mg and Ca have oxidation numbers of +2. So that means for Na or Ag, when you add them to HCl, you're going to get either NaCl or AgCl plus H2. So when you balance this, I'm going to need a 2 here, so I also need a 2 here and a 2 here. So what that means is 2 moles only gives me 1 mole of H2. So what I did is I thought about this being 100 grams. If it's equal masses, I'm going to pick an easy mass, 100 grams. So my Na is about 4 moles. My Mg is about 4 moles. My calcium is about 2.5, and my silver is about 1. But for my Na and my silver, 4 moles is only going to give me 2 moles of hydrogen. And in the case of Ag, it's only going to give me half a mole of hydrogen. But with the Mg and the Ca, because they're a +2 oxidation number, when they combine with HCl, I get MgCl2 or CaCl2 plus H2. So now I only need the 2 here. So this is a 1-to-1 ratio. So now my Mg gives me 4 moles, whereas my Ca gives me 2.5 moles. So now B should produce the most. Number 6 should have been relatively quick. It says you have 4 moles of a hydrocarbon with an empirical formula, CH2, and it has a mass of 280 grams. So the only little catch here is that you have to realize it's 280 grams in 4 moles, which means the molar mass is actually 70 grams per mole. Since it's CH2, we're talking roughly empirical mass of 14. So when I divide here, I get 5 times, which makes my formula C5H10, or letter D. So in number 7, you're told the volume of an ideal gas is 27 degrees. So I want to right away add the 273 to that and plug in 300 as my original temperature. It's increased from 3 to 6, so I'm going to plug that in as well. At what temperature in Celsius? So I need to come up with this in Kelvin, but then I do need to convert it back to Celsius. That's kind of the catch on this one. Will the gas have the original pressure? So I can actually eliminate P from this equation because it's going to stay the same. That's why they don't give us a value. So now I just have to cross multiply and divide. And when I do that, I get 600 Kelvin as my answer, which of course makes D look like a good choice. B also looks like a good choice because you doubled the volume, so you could just double the temperature, but that doesn't work since it's Celsius. So instead, I have to subtract the 273 from this, which gives me C, 327 Celsius. Number 8 wants to know the volume of sulfur trioxide in centimeters cubed. Can be prepared using 40 centimeters cubed of sulfur dioxide or 20 centimeters cubed of oxygen. So what they're really asking is, what's my limiting reactant here? So this one's really pretty easy if you remember that since these are all gases, I don't have to change these to molar amounts. That's why I don't have any more information. I can simply take the 40, look at my molar ratio of 2/2, and expect to get 40 centimeters cubed of sulfur trioxide from the SO2, or coming with the oxygen, it's a 2/1 ratio, and that would also give me 40 centimeters cubed. So neither reactant's limiting, and I can expect 40 centimeters cubed. I don't add these together to get 80 because each one has enough to produce 40. So again, 40 is how much either reactant can yield, but you need both reactants to yield anything. And then another common mistake was people add the 20 and 40 together to get 60. No, you're taking the pieces apart. You need 1 oxygen and 1 SO2 to make an SO3. So that's why the 20 centimeters of oxygen can provide 40 centimeters cubed of SO3, but 40 centimeters cubed of SO2 will only yield 40 centimeters cubed of SO3. Number 5 or number 9 is very similar. I didn't realize I'd put such similar ones back to back. This time I have 5 decimeters cubed of CO, 2 decimeters cubed of O2, and again they're asking what's the maximum volume of carbon dioxide that can be formed. Well, the CO and CO2 have a 2-to-2 or 1-to-1 relationship. So at most the carbon monoxide could produce 5 decimeters cubed of CO2. The O2 has a 2-to-1 relationship, so at most it could produce 4 decimeters cubed. So again, I don't add the 5 and 2 together. I don't add the 5 and 4 together. I simply compare how much each reactant, how much product each reactant could make. And this one makes less, so it limits the reaction to be 4 decimeters cubed. Number 10 was meant to be an easy one for you. 8.5 grams of NH3 is used to prepare a 500 centimeter cubed solution, or right away I just think of this 0.50 decimeters cubed, and the question wants to know which statements are correct. NH3 is the solute, that's true. H2O is the solution. No, the NH3 aqueous is the solution, so H2O is the solvent, not the solution. So that right away brings us down to only C as a correct choice, but let's just double check. The concentration of the solution is 17 grams per decimeter cubed. Yeah, I can see if it's 8.5 in half a liter, this would be 17 in 1 liter. So that's true. And NH3 concentration is 1 mole per decimeter cubed. Well, if I look at NH3, it's roughly 17 grams per mole. And I can either look at my 8.5 and realize I've got half a mole in half a liter, which would give me 1 molar. Or if I look at what I just did in B, I see 17 grams is about 1 mole, and it's in 1 liter. So yes, 3 is also true. So indeed, C is the only statement which is correct. Just 2 and 3 are correct. 1 is false, making C the correct choice. Number 11 is a much easier question than people realize it is typically. You've got 2 solutions of NaCl being added together. So your more dilute solution is going to become slightly stronger. The stronger solution is going to become slightly weaker. I've only got 10 centimeters cubed of the weaker solution, 30 centimeters cubed of the stronger solution. So I would expect my new molarity to be closer to the 0.6, since there's, 3 times as much of the 0.6. So to do this, first of all, I need this in decimeters cubed. I need the original strength. This is moles per decimeter cubed. So I'm going to go ahead and multiply these, and I should realize that this means I have 0.002 moles of NaCl in my first sample of NaCl. My second sample of NaCl, then, I have 0.0300 decimeters cubed. This is at a 0.600 molar strength, or moles per decimeter cubed. So now I get 0.018 moles of NaCl from my second sample. So my final solution, my 2 volumes are going to add up. I'm going to have 0.0400 decimeters cubed. My strength is what's changing, so I don't do anything with that, but I add up my moles and I have 0.020 moles in there. So what's my new strength? Well, I take the 0.020 moles divided by the 0.0400 decimeters cubed, and I see that my new strength is 0.5 molar. And again, that seems reasonable. It should be close to the 0.6. Number 12 is actually easier than it looks as well. What volume in HCl, so 0.2 molar HCl, don't know the volume, is needed to neutralize BaOH2, and this is 25 centimeters cubed of 0.200 molar. So you should notice you've got equal molar solutions here. And then when you neutralize this, you're going to get BaCl2. So what you have to realize is that to balance this, I need a 2 here as well as a 2 here. And so this is in a 1-to-2 relationship. So since they're equal strength, if it took 25 centimeters of this, I could just take that 25 centimeters times the 2/1 relationship, and get my 50 centimeters cubed. Or you could go ahead and take the 25, change it to 0.025, multiply it by the 0.2, calculate how many moles of BaOH2 it is, use the 2-to-1 ratio to get the moles of HCl, and then convert it back to volume. But again, because they're equal strength, I can just directly convert the volumes. This is the idea of M1 times V1, using the molar ratio incorporated in that.